All right, in this video we're going to look at determining the expected value of a probability distribution. So the expected value of a probability distribution is the outcome we would expect to happen if the experiment was performed a very large number of times. In other words, it's a weighted mean of the distribution of outcomes. And we have e of x here, like function notation. We'll use e for expected value of x, is the sum of, remember this is the Greek letter sigma, which means the sum of each outcome of the experiment times its associated probability. So each outcome is denoted with an x times the associated probability for that outcome. Bear in mind that x is a discrete value, so it can only take on 0, 1, 2, 3, so non-negative integer values. So we multiply each outcome by its associated probability and then add those results, and that's our expected value for that probability distribution, which is a weighted mean. So example 3, determine the expected value of rolling 2 dice. So we have here, in our last video, we took a look at creating the probability distribution with each outcome x and each associated probability. Here, I had to split the table up just to have enough space. I wasn't really able to fit it too well vertically in one table, so I split it up into 2 separate tables. And in each one of these tables, I added another column which represents the outcome x times its associated probability. So chances of rolling a 2 was 1 out of 36. So 2 times 1 out of 36 is 1/18th. The chance of rolling a 3 was 2 outcomes out of 36, or 1/18th. So 3 times 1/18th is 3/18ths, which reduces to 1/6. And then we have 4 times 1/12 is a third, 5 times a ninth is 5/9, all the way up to and including 12 times 1/36, which is 12 over 36, or 1/3. So our expected value is going to be the sum of all the entries in the last column. So 1/18th plus 1/6 plus 1/3 plus 5/9, all the way up to and including this last 1/3 here. And when we add up all those values, we get 7. So our expected value for rolling 2 dice is a 7. And again, with probability distributions, if we were to look at the frequencies, for instance, we have 1, 2, we had 3, we had 1, 2, we had 2 occurrences of a 3, we had 3 occurrences of a 4. We could also calculate the mean by listing it all out. That might take a while, but here's what it would look like with a computer. So I'm just going to run this to be able to calculate the results quickly. Here are all the rolls that we can get in that table of values from rolling 2 dice. So we have 2 occurs once, 3 occurs 2 times, 4 occurs 3 times, etc., all the way up to 12. So what we're going to do is we're just going to calculate the mean of this value, this list here, which was our table that we made from rolling 2 dice. And when we get that, we get a sum of 7 from that. And if we were to repeat this experiment several times, like millions and millions of times, and as every time we get a value, a sum, we put it in we mark it down in a list. If we took the mean of that list, of the values in that list, we would get 7 the more times we perform the experiment. Example 4, the distribution below represents the percentage of households that have X number of dogs according to a recent study. So 44% of the households have no dogs, 27% of the households have 1 dog, 18% of the households have 2, and then instead of 3 or more, it just made it 3 because it was too open-ended when calculating the expected value. So 11% of the households have 3 dogs. So what is the expected number of dogs per household? So to calculate our expected number of dogs, our expected value, our mean value, we're just going to take 0 times 44%, add that to 1 times 27%, add 2 times 18% to that, and add 3 times 11% to that. We get about 0.96, which we can round up to 1. So there's about 1 dog per household. So if we were to pick a household at random several times, we would expect to get 1 dog per household, or a little bit less than 1 dog per household, but we can round up to 1 per household. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.